Okay, well, welcome back. And now we're going to just apply what we learned here by working a couple examples. All right. Example 1. Let's say we have y double prime plus 3y prime minus 10y equals 0. Okay. If we assume this looks like y is going to equal e to some root times x, y equals e to the rx, this becomes r squared e to the rx plus 3r e to the rx minus 10 e to the rx, right? It's the second derivative plus 3 times the first derivative and minus 10 times the original function has to equal 0. And once again, I divide through. My e to the rx's all cancel out. And so I'm left with, what do we call this thing? The characteristic equation, which is r squared plus 3r minus 10 equals 0. We can factor this pretty easily. At least I hope we can. Let's see, 10 and 5 and 2 looks like it'll work, but it's minus 10, so it's r plus 3, so it has to be plus 5, and r minus 2 will work out for us. So our two solutions are, our roots are negative 5 and r equals 2. So my two solutions are y1 equals e to the negative 5x. That would work by itself. Y2 would be e to the 2x. That would also work by itself. But to get the full solution, I've got to write out y equals some constant, because any multiple of these would equal 0. C1 e to the negative 5x plus some constant, any multiple of this one would also work, e to the 2x. And that is the general solution for this particular differential equation. All right, that's an example where we have, I'm going to make a note here, orange, two real roots. All right, let's do the next example. Here's my next example. I was looking at the wrong page. 2. Let's look at y double prime minus 6y plus, 6y prime plus 9y equals 0. All right, I'm going to assume the same stuff. Can you guess what my characteristic equation is going to wind up being here? Any guesses what it is? Well, if we go through the same process, we're going to get r squared minus 6r plus 9 equals 0. Now this is interesting, because when we factor this, what do we get? R minus 3 and r minus 3. Okay, well, we have r minus 3 and r minus 3, so r equals 3 and r equals 3. So I could write this out as y equals c1 e to the 3x plus c2 e to the 3x. But these are really the same. Why do I write it like this? Why wouldn't I write it as y equals c1 plus c2 times e to the 3x, which really I could just write as c e to the 3x. Okay, that turns out is wrong. We need to have, if we have a second derivative, if they're second order, we need to have two constants to play with to fit our initial conditions. And we don't talk about y much, but maybe I'll touch on that briefly in class. We need basically two knobs to turn. Right? We need to adjust this equation to fit our initial conditions, right? Like we did in the first order equations. We need two of them. So I write this as, actually I'm going to put an exclamation point there. So I need to rewrite this as y equals, well, c1 e to the 3x plus c2x e to the 3x. And I'm just going to ask you to trust me on this one, since you'll learn about this in much more detail in your Diffie-Q's class, for those of you going into science and engineering and whatnot. Okay, so I'm going to stop this one here as well, because the next one is really long. And, no, what the heck. I'll do it. We'll put it all together. Alright, so the last example. This is going to be a two-pager, so I'm just going to skip, so you can just draw a nice picture here. I want to leave myself room, so you can draw a nice picture here. And maybe during class, we'll have a little, show and tell, who drew the nicest pictures. So this is so this is going to be a two-page example. I bet you can guess which one this is going to be. Example 3, we're going to say that it's y double prime minus 6y prime plus 25 equals 0. All right, now we assume that this thing looks the same, blah, 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 blah. We get the characteristic equation. And this is, let's see, that'll be r squared minus 6r plus 25 equals 0. And that's our, what do we call the characteristic equation. All right. So we factor this one. Let's see, 25. 5 and 5. 1 and 25. Neither of those really give. So, well, we're going to gotta shut down there. Actually, I gotta pause here for just a moment. I'll be right back. All right. Well, the long and short of it here is that this isn't factorable. So we've got to resort to some pretty ugly options here, and that would be this, which should look familiar to all of you. R equals negative b plus or minus the square root of b squared minus 4ac all over 2a, which equals 6 plus or minus square root of, will that be 36 minus 100? Well, there's our problem, right? Negative under the radical, all over 2. And so that will boil down to r equals, I'll save a little bit of time here, 3 plus or minus 4i. Okay, so we have two roots. We have r1 equals 3 plus 4i, and we have r2 equals 3 minus 4i. And remember, these have to be complex conjugates. That's the only way these polynomials work. So my solution is y, well, let me write it this way. y1 then equals e to the 3 plus 4i x, and y2 equals e to the 3 minus 4i x. All right. Now we can start to do a little a little algebra here and write this out. How are we going to write this out? We could say y equals, oh, I forgot the C1 and the C2 here. That's the problem. So that's a C1 and that's a C2. Okay. So we know that e to the 3 plus 4i, right? We can break that down into, remember that will give us a sine and cosine kind of a function. So y equals, this will be C1 e to the 3x, and I think you guys covered this in your trig class, times cosine of 4x plus I sine of 4x plus C2 e to the 3x, and then this will be cosine of 4x minus I sine of 4x. Right? Why is that? Because e to the, if you have a complex root like that, it winds up being a cosine and sine functions. Cosine of, in this case, beta x plus I sine of beta x. Right? So that's how this one works out. So we can do a little algebra here. This just becomes kind of an algebra fest, but I'll run through it anyway. We can distribute this. We have C1 e to the 3x cosine of 4x plus C1 e to the 3x I sine of 4x plus C2 e to the 3x cosine 4x minus, well, that's important, C2 e to the 3x I sine 4x. Alright, and we can combine these. Let's see, we've got e to the 3x cosine of 4x and C1 e to the 3x, C2 e to the 3x cosine of 4x. So that becomes C1 plus C2, C1 plus C2 times e to the 3x cosine 4x. And then we'll collect these two here. The sine terms at C1 minus C2 plus C1 minus C2 of e to the e to the 3x I sine of 4x. And I'm going to kind of rename these C1 plus C2 and C1 minus C2. I'm going to call this one A, and I'm going to call this one B, and then keep in mind we have this I there. Let's not forget that. So when we redo this, we're going to do some more algebra and kind of combining like terms. This part down here, C1 plus C2, e to the 3x, well, I'm just going to make that A, so that's A e to the 3x cosine 4x plus B e to the 3x sine of 4x, and then finally we can do some more rearranging, so that becomes e to the 3x times A cos 4x plus B sine 4x. Now, what happened to the I? Right? Where did this I go? Did I square it? Did I raise to the 4th power or something? No, all I did was I combined the B with I, right? I is a constant, right? It's just we know what it is. It's not a variable, it's a constant, so I can certainly put it in here. So that means that b, note, b is a complex constant. Okay, so it's kind of magical then that we get a combination of exponential and trigonometric functions to solve this differential equation. So that is it. That's it on first or second order linear homogeneous differential equations. We'll look at the non-homogeneous case, which is where we don't necessarily have a zero on this end, which will really mess things up. But we'll look at those tomorrow. Thanks for listening, and have a great day.